many of you do probably. So Charles-André is a research director at CNRS at ParisTech in the south of France. As I can see, he will be talking about grain structures predicted in modeling of additive manufacturing. So Charles-André, please, the floor is yours.
Yes, thank you very much, Roland. And thanks to all the organizers for this invitation. So Manas, Aude and Eric. So today I have associated this my colleague to this presentation, Gilles Daguimou and Oriane Seninger. They are two assistant professors at CMF, so the Research Center for Material Science, located in Sofia Antipolis. It's part of ParisTech, PSL University, and also CNRS. Oh, and of course, Théophile Camus is a PhD student working on this topic of modeling of solidification grain structure in additive manufacturing. So this is the content of the presentation. We will start with a few generalities about solidification microstructures in additive manufacturing, and one of the big part of the presentation will be about using the cellular automaton method to describe or to model grain structures and texture formed during additive manufacturing. And then we will start discussing about what must be developed for these such tools like the kinetics of dendrite tip and the phenomena you can expect when you have rapid solidification. We will see an example of what solidification, virtual solidification grain structure can be used for. Okay, so let's start with this introduction. These are classic relations showing the length scales for primary dendrite arm spacing and secondary dendrite arm spacing, and also the eutectic lamellae spacing as a function of the solidification velocity and temperature gradient G. And basically what you see and what you find in textbooks is that when you increase the temperature gradient or when you increase the solidification velocity, you get a finer microstructure. And so because G times V is the cooling rate, this is a well-known behavior that increasing the cooling rate will lead to finer microstructure. So in the literature, you also see kind of a hierarchy between processes saying that laser powder bed fusion provides with finer microstructure than electron powder bed fusion, LMD, so laser metal deposition, or WAM, wire arc additive manufacturing, and these are these colored circles that you see here. Now, another general trend is about columnar to equiax transition. So you want to know what is the morphology, not only the size of the microstructure, but the morphology of the grain structure. And you can use the Hahn criterion for that, where you say that if the volume fraction of the equiax grain structure reach some value, then you stop the growth of the columnar grains. This is a schematic from the original paper. So you have the columnar grains here. You have the equiax grain growing in the undercooled liquid from the liquidus to the temperature of the columnar front. So you can integrate over time the growth of all these equiax grains, and you get a volume fraction of the equiax grains. These are some simple relations that you can derive. And so you get this criterion that tells you basically that if the ratio between the gradient and the velocity decreases, then you get equiaxed structures. And so this is symbolized by this row here, G over V. If this quantity decreases, you go from columnar to equiax structure. Okay, here I want to show this parameter for the growth velocity of the microstructure, let's say the dendrite tips. You see here, usually it's possible to fit the growth kinetics with a simple function of the undercooling, so the difference between the liquidus temperature and the actual temperature where you are considering the computation of a velocity for the dendritic. So this is a simple power law with A and N as parameter, and NE will be the density of equiax grain here. We will see this parameter again during the presentation. Okay, so now what about additive manufacturing? Well, this is a process where you have a heat source moving on a material that melts and solidifies, at least when you have fusion and solidification involved, depending on the process you consider, but this is very common. And here what I have done is just to draw an analytical solution for the temperature provided by these authors, Klein and Anthony. It's a bit more sophisticated than Rosenthal solution, if you know this one, but it's similar. And so you can, from that, extract the location of the liquidus temperature in red, which is the melt pool. Above this temperature, you have liquid. And here you have the solidus temperature. So below this green isosurface here, at temperature below that value, you have full solid microstructure in principle if you have thermodynamic equilibrium. So this heat source move at a given velocity. Here everything was computed for an Inconel 718. So here you have the parameters for this computation. From this isotherm liquidus isotherm in red, you can extract two things. On the surface of this isotherm, you can extract the velocity, and you can extract on the left the temperature gradients on these isotherms. And you see if you plot the profile from point B, from point A, let's say, to point B, you see that the velocity actually increased from 0 to almost 1000 millimeter per second, 1 meter per second, which is the velocity of the heat source. And this is the green, the red curve here from A to B along the position of this line. You have this evolution of the liquid velocity, and you have this evolution of the temperature gradient, which is decreasing. And so if you take now the product G times V, the cooling rate, as I explained before, it means you expect a finer microstructure toward the B region, where you have at the end of the melt pool, where you have higher velocity for lower gradients, but the product G times V is the highest. And if you now compute the ratio G over V, you see a dramatic decrease of G over V and a chance to get equiax grain, because G over V is very low at the very rear of the melt pool, so toward B. So where is rapid solidification in all that? You know, as you start from 0 in velocity, you have really to define where you want to consider the microstructure, but clearly there is an evolution of the velocity that is very large during this process. Okay, so now we want to do something a bit more sophisticated than analytical solution, because they don't necessarily reflect very well the temperature field. So there is a thermohydraulic model that has been developed solving with finite element method the heat flow, the fluid flow, as well as tracking the boundary between the metal and the gas in order to compute the bead shape. So I'm not going to detail how we do that. There are a few papers already published on that. So, but here is an illustration. You see the color map is the temperature field. You have just below the laser, this is the powder bed fusion process. And below the fusion here, you have a curved liquid gas interface due to the recoil pressure. You see here the shape of the interface in black between the liquid and the gas. Of course, surface tension is accounted for, as well as Marangoni convection. Of course, you see in this liquid region the fluid flow with the rose that is represented. And here, just in front of the advancing laser, you see the powder bed. that is modeled by an equivalent medium. We don't track each particle of the powders here. This is at the end, the final shape of the bead, due to the fact that the powder has a density about twice lower than the substrate and the consolidated track. Of course, there is a variation of the volume of the matter. And so you see here how we finally can predict the shape of the track that has been built. This is an animation. We have removed the powder to better see the construction of the bead. So here you have this green line is the liquid isotherm. So you see how the laser, when it moves from left to right, how you form the melt pool. Here, this is a cross section through, through this simulation domain, where you better see in the transverse cross section the remelted region. The liquid here is actually moving upward in this section, and you could see the formation of the bead at the end. And so you have this final shape of the constructed bead as well as the remelted region in the substrate here. And so with that, of course, we can apply a model to predict grain structure. This is what you have here on the screen. This is exactly on the simulation I've shown before, and it's a 3D simulation, but you have a longitudinal central section through the bead. What you had initially is a grain size that was uniform with no texture in the substrate, and due to remelting and solidification, you form this columnar structure that develops behind the melt pool. Okay, well, so if you do that, it means you are very much dependent on the CPU time you need for the computation of all the thermohydraulic finite element solution. And this solution I've shown you for a 1 millimeter long single track additive manufacturing laser powder bead process is already 7 days of computation, while the CEA simulation was only less than 1 hour. So that's very long, very heavy, very costly. So obviously it will be difficult to have additive process simulated with this methodology. This is why we had to find a solution, and this was done by this PhD student, Théophile Camus. And I'm going to show you what we did. So of course we start with the full thermohydraulics solution simulation, and what we can do is to extract the steady state or steady regime for the temperature field and the bead shape from this thermohydraulic simulation, and we can then apply this extracted field onto a new finite element mesh, so that we know the temperature field and bead shape without solving any any equation, without using the finite element. We just use the finite element mesh to impose a temperature field and a bead shape. Then we can transport these fields according to a predefined scanning strategy for the bead source. For instance, here you recognize the plus x, this is the x direction, so you go to the plus x minus x directions, so as to build layers, and you can do many layers, or you can here have this this cross layer directions for the scan. So here you have plus minus x, but here at the layer below you have plus minus y direction for the scan, and of course you change that with the cellular automaton method to predict the grain structure. Well, when you do that, of course, the hypothesis you have is that you assume that the steady thermohydraulic regime always apply, which you also do if you use an analytical solution, actually. But it's better than an analytical solution because it's the full thermohydraulic regime from which you extract the temperature field and the bead shape. And you also have weak coupling between Fe and Ca, meaning it's a chaining. You take the Fe solution and you import it to compute Ca. So the Ca itself does not bring you information about how you should, for instance, release the latent heat on the Fe computed temperature field. Okay, I'll give you an example of the resources you need for that. So, well, for the finite element mesh, you need something sufficiently with sufficient resolutions. Same for the CA, but for the computation cost now, since you do not do any finite element solution, it's very quick to have a projective temperature field and a bit shape on a finite element mesh. And typically, if you want a 31 millimeter track, that corresponded to 3 full layers of H track of 1.5 millimeter length, this was 20 hours. So you are back to the about 40 minutes for 1 millimeter simulation. This is the result you have many columnar grains at the bottom here of the melt pool here, where the temperature gradient is high and the velocity is relatively low. And at the rear of the melt pool, as I introduced previously, you have low temperature gradient, high velocity. So you have larger undercooling. So you see all this gray region here is actually the undercooled region below the liquidus isotherm in green. And you have more equiax grain forming, and they have time to grow and to block the columnar grain. So you have an equiax zone at the very top rear of the melt pool. Okay, so what I will show you are illustrations with Inconel 718. So the initial temperature, power of the laser, velocity, diameter of the laser, these are actually the parameter you need for the thermohydraulic solution. Then for the macro CA cellular automaton model, you need arch distance 70 micrometer. For this simulation, this first simulation here, we had a 1.3 millimeter length for the scan. Yeah, we had scans 3 layers, and these are nucleation parameters for the equiax grain. So we had a certain density of equiax grain, and very important, as I mentioned before, this temperature velocity relationship with this A and N parameter. And we will see next how we can get access to these quantities. Okay, so yeah, that's an illustration showing how the liquidus isotherm moves in the simulation. This is 10 degree undercooled, 20, 30, 40, 50 degree undercooled. So you have this columnar growth growing, and below the liquidus you may nucleate and grow equiax grain, and of course all these small dots you see here in color correspond to cells that have been captured either by growth or nucleation. Yeah. So now this was one of the very first simulations that was actually done by a PhD student, Théophile Camus. So it's relatively coarse. You will see at the bottom you have this equiax structure. So we melted the structure by moving this bead shape and remelted shape and with the temperature field, and we could compute progressively and grow the columnar structure and equiax structure. So what you see are actually the location where the laser went through. So to better see the structure, we can do Y cross-section. This was transverse cross-section for constant X. So now we can do Y cross-section. And these are typical grain structures. You see these columnar grains forming. At the very top, as I said before, you have equiax grain, but of course they are remelted by the next pass almost. When you're in between two passes, on the right-hand side, you have a coarser columnar structure with more, maybe you don't see it very well now, but you will see later, you have more green colors, that mean more 1,1,0 texture. While here you have more red color and pink color, more 1,0,0 texture. You can do transverse cross-section when considering the grain structure seen from the top. So the initial substrate position was 0 micrometer. So when you do cross-section from minus 50 micrometer, you are almost in the untouched substrate with the initial equiax structure. And when you go up in the grain structure, you can start to see lines here, bands of small grains. You can further go up and check the pole figure here. This is one of the pole figure. What you will see when you are at the very top of this images here that I have put together, so at plus 50 micrometer in the third layer, you can see that you have two strong 1,0,0 direction along plus z, which is at the center of the pole figure, plus z plus y and plus z minus y, meaning that the 1,0,0 main dendritic growth directions are actually 45 degrees away from the constriction direction, the z direction, toward the transverse direction plus y or minus y. And you also have a pole here around the x direction, which is the scanning direction for the 1,0,0 directions. So you have now a very textured material. Okay, well, this is when you push it a bit further, you just continue the simulation. Here the simulation was for a 1 millimeter thick deposit, typically 600 micrometer by 600 micrometer. This is the plus minus x scanning direction. So here you see a Z cut toward the top of this construction, where you recognize what I've just shown, and that was already present at, let's say, plus 50 micrometers somewhere here. Well, if you go at the very top, you have the same behavior as previously with the same texture. It's just a bit more enhanced. And so you can now do cuts. You see here along this A plane. This is the left-hand side grain structure you have. It's all red, meaning that the grain have a very strong 1,0,0 texture. And this corresponds to the fact that the dendrite follow the path of the scan, basically, to make it simple. But if you do a cross-section, the C cross-section in between two tracks, for instance, and this is very coarse grain structure you have here that is very green, and so it means you have a 1,1,0 or 0,11 texture of the material. Something also you can see is that if you do a cross-section in B and C, you'll find more grains because they correspond to the location where you have more equiax grain that were formed and that were not fully remelted by the next layer. And you see that depending if you are in B or in D, you had a plus X or minus X scan of the laser. And as a consequence, you see a slight, you see misorientation of the grains toward the left or toward the right here. So there can be differences. Okay, well, with respect to comparison with experiment, this is a project in collaboration with the Centre des Matériaux, so another research institute of ParisTech. We expect comparisons very soon, so we have result coming. By now, we did not start this comparison, but we believe, according to literature, that we have very representative behavior of the model with respect to texture formation. Of course, you can do the same 10-day simulation using the plus X minus X scanning direction and plus Y minus Y. So you get these different distribution of grains and texture. This is, of course, this is in a Z cut, so perpendicular to the building direction. And this is the overcut. And I believe here I made a mistake. So B will be at the center. Sorry for that. So the B cut here is at the center in between two tracks. So yeah, it's not back here. It's ABC, not BAC. Right. Okay. Well, so far so nice, so good. So, and you find the same comparison with experiment that retrieve the same trend, and you can play with parameters like nucleation density for the AKX grains. So if you change, so what I've shown before was the situation with very high AKX grain density, which you have on the right. So if you decrease the grain density, the AKX grain density, or even if you go to 0, you have this structure, and you see the texture has changed quite a bit, because here you had lots of grain, and now it's more mixed colors, meaning that you have not such a strong 1-0 texture. Yeah, and also the grain size is changing. So here, because you continuously bring new grains that are selected with their orientation, you have a relatively, let's say, fine grains in between. Here they are much coarser, because you only rely on the grains that were in the substrate. So then you have to study the effect of the density of the substrate, and you can also do a single crystal for the substrate and see what's going on if you have nucleation. Then this is what we did, but I don't show it here. Okay, so this was probably an introduction on what grain structure can look like in a simulation using cellular automaton method coupled with finite element heat flow solution. But then we have to discuss how about the parameters, and so how about also the model that we need to compute these parameters. Well, one of the parameters I mentioned previously were this A and N coefficient entering the fit of the growth kinetics law for dendritids. And this is certainly my heavier slide in terms of content, because I didn't want to reproduce all the theory behind what we use. So I just mentioned the principle, and I hope some of you can know that and can follow. So for dendritid that is assumed to be a paraboloid of revolution, we know the steady state diffusion field in the liquid due to segregation of solute, and this was derived by Ivansov in 47. This is what we use. Well, another thing is that you need to know what is the radius of the tip, and for that you can rely on two things. The first thing is the stability analysis for a planar front. So you can derive an equation that corresponds to the minimum wavelength that will destabilize the planar front interface. This can be done for a multi-component toroid. So this was in 2001 by Hunziker. And you can apply then some criterion to decide for the working point of the dendrite tip radius. And this, well, one criterion was proposed in the 70s by Logé and Müller-Kunda. So using all these theories, you can inject this equation into a code that called thermocalc databases to compute equilibrium and to access also diffusion coefficients. And this is what we did. We call this module coupled with thermocalc. It's part of a library we have named Physiology for physical metallurgy models, and where we compute kinetics of dendrites. So we apply that to the 718 Inconel alloy. This is the alloy composition. Some of you will recognize the composition. So it's far from being a dilute alloy. So we have to be careful, because this is the advantage of using thermocalc for all this coupling. You don't need all the dilute solution approximation which you find everywhere. So this is the alloy composition from thermocalc. You of course compute equilibrium, but you can also with a mobility database extract extract a diffusion matrix for all solute elements. And this is done at the liquidus temperature of the alloy. And one parameter which you also need in this model is the interfacial energy that defines for the curvature of the interface. So using these parameters or material parameters, let's say, we can compute this blue curve here coming from the model. And we can see, so this is the undercooling as a function of velocity. So going from 0 to 1 meter in velocity and from 0 to 70 degrees of undercooling. Undercooling means 70 degrees below the liquidus temperature, which I mentioned before, 1340 degrees Celsius for this alloy. And you see that a good fit of this law, power law fit for this blue behavior works well. And this explains why often we use this A delta Tn relationship. This is for Inconel 780. Another thing that you have is the solid tip composition that is computed. If you have no velocity, you are at the liquidus temperature, basically. At the liquidus temperature, of course, the composition of each solute element is given by the coefficient, the segregation coefficient or the partition coefficient at equilibrium. So if you take niobium, for instance, this is the red curve here. Niobium here should be 1.98 for the gamma FCC dendritic phase growing into the liquid. So this is the equilibrium value of composition at the liquidus for 0 velocity. But if you increase the velocity from 0 to 1, actually there is an increase. You don't see it very well because it's a log scale. I wanted to have all the solute spaces on the same graph, that's why. But here the composition of niobium for 1 meter per second reaches more than 4 weight% copper, weight% niobium, which comes closer to the nominal composition. And this is just because of increase of solubility of niobium when you decrease the temperature. And despite this, what I want to say is that here we assume full interface equilibrium, meaning there is no kinetics effect on the phase diagram. That's an important point. So these variation of composition are just due to supersaturation that increase with velocity by decreasing temperature, assuming equilibrium at the interface. So now comes the question, what about the effect of rapid solidification? Because you can imagine that at 1 meter per second, we may start to have effect that makes the solid liquid interface departing from thermodynamic equilibrium. And this is what is observed recently. It's known for a while, but now we have in situ observation of the growth of a solid liquid interface up to 1 meter per second. And for that, this author used a technique I don't know very well, but it's transmission electron microscopy, what we call the movie mode dynamic transmission electron microscope. So they can image here the boundary between the liquid and the growing structure. It is an elliptic shape. So they have a minor and a major axes. So they can follow the velocity of the minor and major axes, and you see the average of the velocity in red going from almost 0 to 1.2 meters per second. So in stage 1, they identify several stages, and they do images about every 2.5 microseconds. So it's not fast enough to have a real movie, but it's already quite an achievement, I believe. And so they can measure then, of course, the composition of the alpha dendrites or cells microstructure forming. So at the beginning, for low velocity, they have a relatively low composition of copper. I did not say this is aluminum copper, and so you form alpha aluminum rich cells and dendrites as primary solidification microstructure. So the composition is relatively low, 3.4 weight% atom percent copper. It goes up to 7 atom percent in this small layer here. Then when you go in this part of the microstructure, they name it zone 3 from here to here, they see an increase of the copper content in the alpha cells from 7 to 10.3. And then they get this bending microstructure in the zone 4, which is the highest velocity here at more than 1 meter per second. And again, you see that the alpha aluminum cells have an increased composition of copper. And this cannot be explained by just increased undercooling and increased solubility of copper in alpha aluminum. So to explain that, you need to account for rapid solidification phenomena that are known as solute trapping. So if you have equilibrium, thermodynamic equilibrium, what we consider is that the solute atoms have time to diffuse away from the interface. So basically, if you consider diffusion in the liquid divided by the velocity of the interface, this quantity is much larger than delta, which is the thickness of the diffuse interface. And as a result, you see here these black atoms, these are the solute atoms B. They are in the liquid on the right, in the crystal solid on the left, and they redistribute due to solidification following equilibrium at the interface. And this is the way you have the equilibrium phase diagram. So you have less B atom in the crystal compared to B atom in the liquid. And this happens with thermodynamic equilibrium, meaning you have equilibrium potential of the atoms in solid and liquid. And you retrieve the segregation coefficient given by the thermodynamic equilibrium. Well, when you have departure from equilibrium, the atoms do not have time to diffuse away from the interface that moves at velocity v. So d over v is now much lower than delta, this interface, this thickness of the diffuse interface. And so the atoms are trapped in the solid. This is what we call solute trapping. And in this situation, the chemical potential of B atoms in solid and liquid are different. And in the extreme situation, the composition of atoms in the solid and in the liquid are the same, which you see here, equal composition in solid and liquid, but it means you have a different chemical potential in solid and liquid. Okay, so the extreme situation actually corresponds to the situation where instead of using, this common tangent line construction for the free Gibbs energy of solid and liquid curve, instead of doing that, you actually take the equal value of the free energy of solid and liquid. And here you have solid and liquid composition that are equals, and this gives you what we name the T0 line. So this is T0 line is part of it's an information that is part of the phase diagram. I don't go into the detail of that, but the message I want to give is that most often in the literature, you find a coefficient, segregation coefficient that is represented or it is computed with this expression, a segregation coefficient equal to the nominal or equilibrium segregation coefficient plus the Peclet due to the velocity of the interface divided by 1 plus Peclet. And this Peclet number is delta V over D. So delta will be a thickness of the diffuse interface, V the velocity, and dl the liquid diffusion, or the typical diffusion coefficient within this diffuse interface. So if the velocity increases enough, all this quantity tends toward 1. And similarly, you have expression for the slope of the of the liquidus that change with velocity. These are approximation. So if you take the silver-copper phase diagram, this is liquidus, this is solidus, and these are the two expressions I've shown before. mv, this is the slope for a given velocity. This is using kv, the segregation coefficient for a given velocity. So the slope is here. Here is mv over kv for the solidus. And this differs from, of course, the liquidus line and the solidus line, assuming here ideal dilutes or linear approximation. Well, I don't go into, I don't explain now the presence of kinetic undercooling. We'll see that next. And this is the T0 line that you can compute directly with the property of the phase diagram. So you see the T0 line is actually quite different from this linear approximation. And similarly, you can say the liquidus line, of course, is very different from this linear approximation. So it's important not to consider this linear approximation for multi-component. So for that, there is a methodology that exists. And I don't think I have time to go into the detail because I see time is going. But you have a liquid with this composition here, with this free energy, and you want to transform it into a solid with this free energy. So this is the driving free energy. And this driving free energy can be linked to the velocity using the continuous growth model by Turnbull in '62. And you can also add an equation to describe how, well, the partition, how solute and solvent atoms will partition at the interface. This is a model by Aziz and Kaplan. And so you have these two equations, and you can use these two equations to compute the kinetic phase diagram. So this is what you have here. Unfortunately, I have to be a bit fast. But you see here at low velocity and higher velocity, how the phase diagram, liquidus and solidus lines will change. At low velocity, the red curve here is actually almost superimposed with the liquidus of the alloy. Here in this region, the solidus also is superimposed, but not in this region here where you have this metastable solidus line. It's a retrograde solidus line. And when you increase the velocity, the liquidus and the solidus line, they merge together toward the green curve, which is the T0 line. And you finally have almost no segregation, which means segregation coefficient is equal to 1. If you go to much higher velocity now, what happens is that you, in addition to having this solute trapping mechanism, you have this large kinetic undercooling. And so the liquidus and solidus line have changed drastically compared to what you had at equilibrium. This is an animation showing the evolution of liquidus and solidus line when you increase velocity. So first they converge toward a single line, meaning you have no segregation. This is solute trapping. And then you have the kinetic undercooling that is added. So my message here is that we need to extend this methodology for multi-component alloys in order to be able to have a solute trapping effect on the growth kinetics and to have correct growth kinetics for this microstructure. So it's not just about computing colors with grain structures, right? We need to have good kinetics, and this is not done. This is I believe, one of the challenges to do that for multi-component coupled with CalFAT databases. My last transparency before conclusion is about why we should do a virtual solidification grain structure. There are several reasons. One of the reasons I believe is that we can better study mechanical behavior directly from virtual structures. And this is a work done by my colleague Yansheng Zhang in collaboration with Michel Belay. They have directed Feng Gao, another PhD student who will defend in few weeks from now. And you see, giving this computing microstructure using the CA model, they can input this into solid mechanics solvers to do uniaxial tension test along the X direction, which is the scanning direction, or along here the Y direction, and they also did along the Z direction. I don't show that, so you can predict the distribution of stress and strain in this sample, and you can rebuild stress strain curves depending on the direction for the uniaxial tension test. And this, of course, is interesting because you can directly access to the mechanical properties from the virtual microstructure. Okay, I want to conclude very quickly. I see I am out of time very soon. So, yeah, you can do café simulation of grain structure. One of the challenge thought is the CPU time. Actually, using 28 processors unit, it took about 1 hour for 1 millimeter. In the big simulation I've shown you were 10 days. And this only represents a small volume of, let's say, less than 1 cubic millimeter. So if you would like to do a computation for 1 cubic centimeter component by additive manufacturing, which is already quite small, but let's imagine this is of interest for you, you will need 76 years of computation. So my message is that it's probably not reasonable to think about having a full component, or maybe, of course, it must not be a dense component, and we have to find ways to change that. For dendrite tip, we need to generalize for multi-component alloy the kinetic undercooling due to solute trapping, and we need more validation with dedicated experiment. I think this new in situ observation or something really unique for that. I hope we will have more. What for this computed structure? I've shown you an example on using this mechanical, this grain structure to compute mechanical behavior. Actually, there are other reasons why we want to have solid mechanics coupled during the formation of the structure. This is to model hot tearing, intergranular segregation. And we start in another project on welding to have also use of this grain structure to compute acoustic wave propagation for in situ non-destructive and diagnostic. Okay, so with that, I know the time is now past. So thanks a lot for your for listening. I'm happy to answer questions if there is time for that. Thank you.
Thank you very much, Charles-André. Very detailed and interesting explanations on how we can deal with these solidification microstructures. Yeah, we are a little bit lacking time, but maybe one short question before going. And then after that, we can come back, of course, to more questions after the three presentations have been done. We have like 30 minutes left after that for more questions. Yes, Aude, one question. Yeah.
Yeah, my question is a long one, so I'm going to ask another one, and I'll keep the long one for later. In the hydraulic simulation, how do you account for the properties of the powder?
Yeah, well, I would have needed half an hour to explain in detail this model.
Okay, we don't have half an hour. So that was a short one.
No, but so we have an equivalent medium, and so of course one of the main things is the thermal conductivity of the powder. So we have a model that as a function of porosity and size of the powder gives you the equivalent thermal conductivity. And for the heat capacity, we have half porosity or half gas, let's say, and half powder. So we just average the heat capacity.
So it's some kind of a composite model, air powder then.
Yeah. So it's an equivalent continuum media for the powder.
Thank you for this very interesting presentation. My main question was about a possibility to predict cracking, but I think we'll discuss that at the discussion time. But because I think other people might be interested in having a long answer to that. Thank you very much. Very interesting presentation. Very nice one.
Thank you. Just maybe a little quick compliment on the powder aspect. Do you have a heat source then which is becoming not on the surface but volumetric when you have powders, and the fact that you have the laser beam going into the powders and scattering within the powders?
No, no. So well, there is a heat source, and we consider interaction between the heat source and the powder and the liquid, but there is no. We do not directly simulate, by ray tracing or the laser diffusion.
Yeah, sure.
From one particle to the other, and this is not possible with this methodology. Yeah. So what we have absorptivity for the various part of the dense material, powder and liquid, let's say, and of course all this then needs to be adjusted. So we have comparison of remelted shape, depth, width. And this is in the publication that I mentioned. So this can be
okay.
Well, yeah, adjusted.
All right. Thank you very much, Charles-André.